Hey everybody, here are the notes for homework 13, which deals with composition of functions and inverse functions and a few related items. So let's look at some examples because really that's kind of the best way to see how a composition works. So let's say we're given that f of x is equal to 3x plus 1 and g of x is equal to x squared minus 2x. First of all, we can evaluate f and g at any value of x because, well, I'll point out that f and g have a domain of all real numbers. There's no fractions, there's no logarithms, there's no even roots. So any real number is valid here. So for example, if I want to find g of 5, I can just plug that in there and get 5 squared minus 2 times 5, which is 25 minus 10, which is 15. Or g of 4 would be 4 squared minus 2 times 4, which is 16 minus 8, which is 8. F of 5 would be 3 times 5 plus 1, which is 15 plus 1, which is 16. F of 4 would be 3 times 4 plus 1, which would be 12 plus 1, which is 13. G of 8 would be 8 squared minus 2 times 8, which is 64 minus 16, which is, I think, 48. And finally, f of 8 would be 3 times 8 plus 1. Right, we're just substituting in whatever value is in the parentheses for x in whichever function we're looking at. That'd be 25. Okay. We can also evaluate the composition f composed with g, which I never write it this way. Some people say f circle g, some people say fog, but it's f composed with g for any value of x. Please note that you can say f composed with g of x, which is terrible, or you can do the much, much better f of g of x, which is how you should say it. And I do recommend saying f of g of x. Those ofs are really important when you're thinking about what's going on in your head. So for the same functions, and again, I'll write them over here just so we have them kind of on reference for f of x equal to 3x plus 1 and g of x equal to x squared minus 2x. I want to find f of g of 4. So if I was doing this, I would work from the inside out. So I would say, okay, g of 4. So g of 4 is going to be 4 squared minus 2 times 4. So f of g of 4 is going to be f of 4 squared minus 2 times 4. Right, the inside there is my g of 4. So I'm going to point that out. I'm going to simplify that. I already did it, right? G of 4 up there was equal to 8. So that's going to be f of 8. And then f of 8, I'm going to plug that back into the f of x function. I'm pointing in the wrong place here. F of 8 is going to be, well, I did that one too, right? F of 8 was 3 times 8 plus 1, which is 25. So f of g of 4 is the same as f of 8, which is 25. Let's go the other direction. The reverse, or in the reverse is better, yeah. G of f of 4. Well, let's see. F of 4 was 13. So I'm going to do g of 13. And then g of 13, that's going to be kind of big. So again, g of x is x squared minus 2x. So g of 13 is going to be 13 squared minus 2 times 13. 13 squared is 169. So we get 169 minus 26, which is 143. Again, the point here really isn't the actual numbers, but the point that we're doing the inside function first, f of 4, and then applying g to the result. Let's look at something where we don't actually have numbers. So if I want to find, say, f of g of x, that'd be f of, well, let's see, g of x is the function x squared minus 2x. So then f of x equals 3x plus 1. So f of some stuff is going to be 3 times that stuff plus 1. You could leave that as is, or you could simplify it depending on the problem. If I multiplied that, I'd have 3x squared minus 6x plus 1. Let's look at the reverse composition, g of f of x. Again, I'm always working from the inside out. You don't have to do that, but I think it's the best way to do it. That's going to be g of 3x plus 1. And then I know that g of x is x squared minus 2x. So g of some stuff is going to be the stuff squared minus 2 times the stuff. We can simplify that. That's going to, and then we plug in the stuff, right? 3x plus 1 squared minus 2 times 3x plus 1. The simplifying isn't super important here, although it's good to be able to do. If you multiply this out, it's going to be 9x squared plus 6x plus 1. And then minus 2 times 3x is 6x. And the minus 2 times 1 is minus 2. And then simplifying, the 6x's actually end up canceling out here. And we get 9x squared, and then 1 minus 2 is minus 1. Cool. We can even compose a function with itself. So g of x is going to be g of x squared minus 2x. And then just like before, g of some stuff is the stuff squared minus 2 times the stuff. G of some stuff is the stuff squared minus 2 times the stuff. Again, it's more important to be able to kind of get to here, but if we did want to multiply this out and simplify, x squared minus 2x quantity squared is going to be x to the fourth minus 4x cubed plus 4x squared, and then distributing the minus 2 here, minus 2x squared plus 4x. If we combine like terms, I think I can squeeze this in here. It's going to be real close here. I don't know. X to the fourth minus 4x cubed. 4x squared minus 2x squared is plus 2x squared. And finally, plus 4x. I feel real bad about how small I'm writing that, but that's what we've got. Let me zoom in real quick so you can all see that. That was an x to the fourth minus 4x cubed plus 2x squared plus 4x. But again, it's more important to be able to get to just this first stage right here, where you're just inputting the inside function to the outside function. Zoom back out. Okay, let me make sure my camera angle is good here. Sorry, yeah, there we go. Okay, next page. So composition is just a function of a function. Definition: the functions f of x and g of x are inverse functions if f of g of x equals x and g of f of x equals x. In other words, f of x and g of x are inverse functions if they undo each other. So the way I think about this really, right, if f of g of x is equal to x, that means g did something to the x value, and then f of that undoes what g does and gets you back to the x value you started at. Let's look at some examples. So I'll start off by saying that f of x equal to 3x plus 2 over 7 and g of x equal to 7x minus 2 over 3 are inverse functions. And we will show that. But I just want to point out that you can kind of think about how these functions are undoing, I really like the word undoing here, what the other one does. So the function f of x takes your input of x, multiplies by 3, then adds 2, then divides by 7. G of x does exactly the opposite in the opposite order. G of x takes your input of x, first multiplies by 7 to undo the divide by 7, then subtracts 2 to undo the adding 2, and then divides by 3 to undo the multiplication by 3. Let's look at some examples here. So if we look at f of g of 2, well, g of 2 is going to be 7 times 2 minus 2 all over 3, which is right there. 7 times 2 is 14. 14 minus 2 is 12. 12 divided by 3 is 4. That's going to be equal to f of 4. We plug 4 into the function f. F of 4 is going to be 3 times 4 plus 2 divided by 7. 12 plus 2 is 14. 14 divided by 7 is 2. So look, g did something to 2, right? I'll just point out here that g of 2 was equal to 4, and then f of 4 got us back to 2. And that is the whole nature of inverse functions, is that the inverse functions undo what the other function did. Let's look at a couple more examples. So I'll point out here that although we're going to do this the long way, the whole point of something like g of f of 11 is that we know that if f of x and g of x are inverses, then they should undo what the other one does. So I'm not going to write right there for a second. I'm going to write below here. I want to find out what f of 11 is. So f of 11, if I take my f of x function, that's going to be 3 times 11 plus 2 divided by 7. That's 33 plus 2, so 35 divided by 7, which is 5. So then g of f of 11 should equal g of 5, because we just found out that f of 11 was equal to 5. And then g of 5, if we plug 5 into the g function here, that's going to be 7 times 5 minus 2 divided by 3. That's 35 minus 2, so 33 divided by 3, which is in fact 11. Which isn't surprising because we knew that g and f were inverse functions. So g of f of something should end up being just the something that we started with. I'll say it again, inverse functions undo each other. So for both of these here, we are expecting that f of g of x is going to equal x and the g of f of x is equal to x. Let's actually do it though. So f of g of x is going to be f of 7x minus 2 over 3. It's going to be a little bit complicated here, a little bit, just a little bit tight. So we're going to plug that into our f function. So we're going to do 3 times our parentheses plus 2 divided by 7. Then we're going to plug in the parentheses, so that's going to be 7x minus 2 over 3. I do recommend when you do this that you don't just cancel everything at once because it's a little bit dicey. So I'll point out that the 3 divided by 3 here does cancel. And I'm going to write out the next step as 7x minus 2 plus 2 divided by 7. We definitely should cancel the 2's next because negative 2 plus 2 is 0. And then we're going to get 7x divided by 7, and the 7's cancel, and we just get x. As expected, f of g of x is equal to just x. G did something to it. It gave us 7 times x minus 2 divided by 3. F undid that and took us back to where we started. Same deal here. I recommend you all try doing this one on your own before I do it. So pause the video, get pencil out, try doing g of f of x. So let's see here. So g of f of x is going to be g of f of x, which is 3x plus 2 divided by 7. We're going to plug that into the g function. That's going to be 7 times parentheses minus 2 over 3. Then we plug in the 3x plus 2 over 7. 7's cancel. We get 3x plus 2 minus 2 divided by 3. The 2's cancel. We get 3x divided by 3, and that is equal to x. So yes, it works both ways. You do have to check both ways if you're asked to show the functions are inverses, because occasionally it'll work one way and it won't work the other way. There's a very kind of well-known example that we'll talk about in a little bit here. Something to note that if we call f of x equal to 3x plus 2, then the inverse we call f inverse of x, and we write it as f with a -1 superscript of x. But we do read this, we don't write it as, or say it as f to the -1, we say it as f inverse of x. So we call f of x equal to 3x plus 2 over 7, and g of x we call f inverse of x equal to 7x minus 2 over 3. A couple other notes here. If f of x is equal to y, so if you input some x and you get out some y, then f inverse of y should equal x, meaning the input here and the output here interchange for the input here and the output here. So inverse functions interchange the relationship between input and output. So for example, if we knew that f of -3 was equal to -1, which it is, right? If you actually take this function here and plug in -3, I'm still using the same function. F of -3 is 3 times -3, so -9 plus 2 is -7. -7 divided by 7 is -1. If f of -3 is equal to -1, if f of -3 is equal to -1, it should be obvious that f inverse of -1 is equal to -3. We can also plug it in though, right? If we actually look here, f inverse of -1, if we plug it in, is going to be 7 times -1 minus 2 over 3. That's -7 minus 2, so -9 divided by 3, which is in fact -3. But the real point here is that we didn't have to do that work to know that that was going to be the answer. If f of something equals something else, then f inverse of the something else should equal the original something. Again, I can't say it enough. Inverse functions undo each other. Inverse functions invert the role of the input and the output, the x and the y. Okay. Which leads to kind of how we find an inverse function. So just as I said before, I'm going to say it again. Inverse functions interchange or reverse the role of x and y. So if I want to find f inverse of x for, say, the function f of x equal to 3x plus 5, here are the 4 steps. Step 1, we usually like to write it as y equals 3x plus 5. That's not really much of a step, but it is worth doing. Step 2, interchange x and y. So we're going to rewrite this as x equal to 3y plus 5. Again, not really doing a lot of work here, but at this point you actually have inverted the function. So you've changed it to something else, the inverse. And then we have to solve for y. I will point out some people like to do this step before doing that step. It doesn't really matter which way you do it, as long as you both solve for the other thing and then interchange. So you could have done this first solving for x and then interchanging x and y afterwards. So solve for y, so subtract 5, x minus 5 equals 3y, and then divide both sides by 3. So x minus 5 divided by 3 is equal to y. And then finally, and this last step is kind of again, not super necessary, don't write it as y equals x minus 5 over 3. Write it as f inverse of x equals x minus 5 over 3. And again, I'll point out that just like, and again, for these linear ones, it's kind of easier to see that they really are undoing what the other one does. This function takes an input of x, multiplies by 3, and then adds 5. This inverse function undoes that by first subtracting 5 and then dividing by 3. So you're exactly undoing the things you did in the opposite order. So let's look at the function we have been looking at, the f of x equal to 3x plus 2 over 7. And although we already know the inverse was, what was it before? The inverse function is 7x minus 2 over 3. Let's go ahead and show the work for finding it. So step 1, rewrite it as y equal to 3x plus 2 over 7. Step 2, interchange x and y. So you're only going to have one y become an x. You might have multiple x's all become y's. So x equals 3y plus 2 divided by 7. The next step is where you actually do the work. We're going to solve for y. So I'm going to multiply both sides by 7. So 7x equals 3y plus 2. Subtract 2 from both sides. So 7x minus 2 equals 3y. That is a y. Sorry, that's kind of gross. And finally, step 4. Oh, no, I'm not done with the step 3. Sorry, divide by 3. So 7x minus 2 divided by 3 equals y. And then finally, we're going to write this as f inverse of x equals 7x minus 2 divided by 3. Just like we knew it was. Here, we'll do like 4 or 5 more examples of this because it's kind of an important thing to be able to do. So let's find the inverse of g of x equal to 2x cubed minus 5. Same 4 steps. I will point out that typically, as long as your polynomial that this function is equal to is only odd powers of x, it's usually pretty safe to kind of just do what we're about to do. We'll talk about an even power example a little bit later. So step 1, write y equals 2x cubed minus 5. Step 2, interchange. X equals 2y cubed minus 5. Step 3, start solving for y. So x plus 5 equals 2y cubed. Divide both sides by 2. Or you could also multiply both sides by 1/2. So instead of writing x plus 5 divided by 2, you could write 1/2 times x plus 5. Both are fine. Finally, undo a third power by taking the cube root of both sides. So the cube root of 1/2 times x plus 5 is equal to the cube root of y cubed. Odd powers and odd roots do undo each other, right? There's no absolute value weirdness. So here we can just write that this is y equal to the cube root of 1/2 times x plus 5. So finally, step 4, we can write our final answer as g inverse of x equal to the cube root of 1/2 times x plus 5. Or if you prefer, you can write it as x plus 5 over 2. And instead of writing it as a cube root, you could write it as to the 1/3 power. Either way would be totally acceptable. Cool. Let's do the next one. I'm going to do the next one in the slightly different way. So for this next one, just to show you all that you can do it either way, I'm still first going to write y equals 4 over x to the 5th plus 1. But now I'm going to change the order of solving and changing. So instead of interchanging x and y first, I'm going to solve for x first. So solve for x, meaning isolate x. So subtract 1 from both sides. So y minus 1 equals 4 divided by x to the 5th. Multiply both sides by x to the 5th. So we're going to have x to the 5th times y minus 1 equals 4 over x to the 5th times x to the 5th. And the whole reason we did that was to get rid of the denominator because those x to the 5ths divide to 1. And then we're going to, I'm trying to solve for x here. So I'm going to divide both sides by y minus 1. So then x to the 5th equals 4 over y minus 1. And then finally, take the 5th root of both sides. So that x is equal to the 5th root of 4 divided by y minus 1. I really don't like doing it this way. I feel like that was terrible, but it's fine. So then the third step here is to interchange. So now we have y equal to the 5th root of 4 over y minus 1. And then finally, rewrite it as f inverse. Oh, sorry, you can't quite see that. Apologies. F inverse of x equal to the 5th root of 4 over y minus 1. Or if you prefer, 4 over y minus 1. Sorry, I didn't actually interchange. Good job, James. Sorry about that. If I interchange, I should be changing the x to a y and the y to an x. Sorry about that. Yeah, so clearly I like doing it the other way, where I interchange first and then solve for y. So I interchange here, I should have written this as the 5th root of 4 divided by x minus 1. And so here, I should actually be writing the right thing, which is that f inverse of x is either equal to the fifth root of 4 over x minus 1, because if the inverse function is a function of x, we should be writing it as a function of x. Or we can write it as 4 over x minus 1 to the 1/5 power. Either way is totally fine. It definitely needs to be x's, not y's. So yeah, you can totally do it that way if you like. If you like solving for x first and then changing the x's to y's and the y's to x's, that's fine. Obviously, that is not the way I prefer to do it. Okay, let's look at some more examples. Find the inverse of f of x equals 6 to the x minus 2. So again, we're starting off by writing y equals 6 to the x minus 2. We're interchanging x and y. So we're writing x equals 6 to the y minus 2. And we have to solve for y. And there's a couple different ways you could go here. You can either use log base 6 or natural log. Either way is totally fine. I don't know. I don't really have a preference here. I'll show both. So one way to do this would be to say, okay, I'm going to do the log. So actually, sorry, let's start solving for y. So first I should add 2 to both sides. So x plus 2 equals 6 to the y. And then I know I can rewrite an exponential equation, 6 to the y equals x plus 2 as log base 6 of this stuff is equal to the exponent. And that's kind of it. So one way of writing our answer would have been to say that f inverse of x is equal to log base 6 of x plus 2. Alternatively, from this step here, we could have said, if I have 6, I'm going to rewrite it with my y on the left, 6 to the y equals x plus 2. I could take the natural log or the log base 10 on both sides, or whatever log you prefer. So you can say, great, natural log of 6 to the y equals the natural log of x plus 2. The y comes down. So y times natural log of 6 is equal to the natural log of x plus 2. And then divide both sides by the natural log of 6 to get y equal to the natural log of x plus 2 divided by the natural log of 6. So it would be as good, as correct to write that f inverse of x is equal to the natural log of x plus 2 divided by the natural log of 6. Both are correct, both are equivalent. Either way is fine. Take your pick. Although on your homework assignment, there might be limited options. Like it might look like this instead of looking like this. So basically make sure you're aware that you can get there either way. And depending on what your multiple choice answers are, you might have to look at this way versus that way. Okay. So now we're kind of going the other direction. If we want to find the inverse of a logarithmic function, we're going to probably end up with an exponential function. But again, the process is the same. So start by writing y equals whatever f of x was, log base 3 of x plus 1. And then we're going to interchange x and y first because I like interchanging first. You don't have to do it the same way I do it. Isolate y. So before we can isolate y, we have to isolate the function that y is in. So I'm going to isolate the log of y. So I'm going to have x. Oh, sorry, that's step 3 is to start solving. Sorry. X minus 1 equals log base 3 of y. And then rewrite it as a base of 3 to the power of x minus 1 equals y. And we're pretty much done. That's kind of it. So you don't really have as many options here. So here our inverse function, g inverse of x is equal to 3 to the x minus 1. Cool. Oh, I should put in the code that I haven't thought about yet. So the code for the homework, if you want to start doing it before it's released on Wednesday. Let's see, the code is one of my favorite numbers. It is 1,331. 13 for homework 13 and 1,331 because it's 11 to the third power. So just a 4-digit code, all numbers, no letters, 1331. Cool. All right, and there it is again. So this is the access code for homework number 13. Cool. Again, it'll be available Wednesday, I think, at 11. All right, so here's kind of a more kind of, what's the word I'm looking for here? Specific case where you have a function who we want to find the inverse of, but well, we're limited here. This function actually requires some talk. So if you look at the function f of x equal to x squared plus 9, It's a typical parabola shifted up 9. And the hard part here is that if you look at a parabola, it looks like this. This function actually isn't invertible as is, because if you try to interchange x and y, look what happens. So here's, y equals x squared plus 9. If you interchange x and y, you're going to get x equals y squared plus 9, which I'll point out is a right opening parabola. You can plot some points. If y is 0, x is 9. This is the point 0, comma 9 here, where x is 0, y is 9. But here they flip, so instead of getting 0, 9, you get 9, 0. And then I put that in a really bad place because my parabola is going to look like this. It'll look like that, and like that. Sorry, I know it's terrible. So for example, I'd also have the point here. If x is 1, y is 10. If x is negative 1, y is also 10. Here, the reverse, or the inverse. If y is 1, x is 10. And if y is negative 1, x is also 10. And the thing here is that in this particular example, the inverse relationship isn't a function. It fails the vertical line test. I can put in one x value and get two different y values, which is a no-no. Sounds like a dumb thing to say, James, which isn't good. Makes it, well, it's not that it's not good, it makes it not a function, right? This fails the vertical line test. So what do we do? Well, if we want a function that isn't invertible to be invertible, we restrict its domain. So this function, this original function, which is a function, the reason it's not invertible is because it fails the horizontal line test, which is the same as the vertical line test except with horizontal line. So if you can draw a horizontal line through more than one point, it's not invertible. It's still a function, not invertible. But we'd say that this function, f of x equal to x squared plus 9, is not 1-to-1, which people often abbreviate as just like a 1-1. That means that there are different x inputs that have the same y output. And for a function to be invertible, it needs to be 1-to-1. So for f of x to have an inverse, it needs to be 1-to-1. It's kind of a requirement. So what we do for functions like this, and there's actually a very special class of functions that we get to later on that we really, really want to be invertible that aren't, and so we do this for them. But for this example, what we're going to do is we're going to take this function, f of x equals x squared plus 9, and we're going to restrict our domain to where x is non-negative. So if I graph this again, I'm only going to have the part where x is greater than or equal to 0, which is that half right there. Sorry, where x is greater than or equal to, and that half is invertible, right? It's got a domain, sorry, it's 1-to-1, right? It passes the horizontal line test. It's got the point, 0, 9, and the point 1, 10. And if we draw its inverse, well, I'm really just interchanging x and y. So I'm going to get the point 9, 0, and 10, 1, and it's going to look like that. It's going to look like the top half of this rightward opening parabola. So here's how we're going to solve for it. So I'm going to take my function. Sorry, I know there's a lot going on here. So my f of x equal to x squared plus 9. I'm going to do the usual thing, but I'm going to remember that x has to be bigger than or equal to 0. Okay, so check this out. It's kind of weird. First step, rewrite it as y equals x squared plus 9. I do think it's good to include the domain restriction along the way. Okay, so here's what's going to happen. We're going to interchange all the x's and y's. So I'm going to get x equal to y squared plus 9. And now I'm going to say that y has to be greater than or equal to 0. Every x, including the one in the domain, changes to a y. So now this domain restriction for my inverse function becomes a range restriction. Kind of strange. But then we carry on. So I'm going to solve for y. So I'm going to get x minus 9 equal to y squared. Y still has to be greater than or equal to 0. And then y is going to equal, so normally it would be plus or minus the square root of x minus 9. I'm going to take a square root, you stop on a plus or minus, but we know that y has to be bigger than or equal to 0, so y can't equal the negative square root of x minus 9. So it has to be only the positive part. which is why we're only getting the top half, right? But that looks like a square root function, not a negative square root function down there. So our inverse function here is f inverse of x equal to the positive square root of x minus 9. And I no longer have to write that y is greater than or equal to 0 because writing a square root like this already implies as much, that it has to be greater than or equal to 0, my output. So there's my inverse function, which exactly looks like what I've graphed here, right? It's my square root function, but it's been shifted 9 to the right. So my starting point is 9, comma 0. I've got this other point here, 10, comma 1. So that's how we deal with functions that don't start off as being invertible. We restrict them to just a portion where they are invertible or one-to-one, and then do it. Kind of weird. All right, let's look at a few more things here. Right, so just as I was saying, functions are invertible if and only if they are 1, 2, 1. AKA, they pass the horizontal line test. And the reason they have to pass the horizontal line test is so that when you interchange x and y, that horizontal line that becomes a vertical line and it passes the vertical line test. I should say the inverse passes the vertical line test. Interestingly, we can graph the inverse of a function simply by interchanging the x and y coordinates of each point, which I kind of did in that previous example, right? In the previous example, I plotted a few points, 0, 9, 1, 10. I could have plotted, the point 2, comma 13. And over here, I could have plotted the point 13, comma 2. But exactly, since you're literally interchanging x and y, when you're graphing things, you can literally interchange x and y. How convenient. So over here, sorry, papers, I'm going to graph f of x equal to 2x minus 3 by plotting the intercepts as I usually would, and then I'm going to graph the inverse by plotting the intercepts. So my y-intercept here, if I set x equal to 0, I would get f of 0 equal to 0 minus 3, which is negative 3. So my y-intercept is 0, negative 3. So here's my y-intercept on my original function, f of x. My x-intercept, if I set y equal to 0, or f of x equal to 0, I get 0 equal to 2x minus 3, 3 equals 2x, 3 over 2 is equal to x. That's going to be about right there. And I guess I should use a ruler because it's good to draw your straight line straight. So here's my original function, f of x. Okay, so now I'm gonna label these. So this is the point 0, negative 3. This is the point positive 3 halves, comma 0. To graph the inverse function, instead of finding the inverse, although we totally could find it, and we will in a second, we're just going to graph the inverse by plotting the inverted points. So instead of 0, negative 3, I'm going to get negative 3, comma 0. Right? Interchanging the x and the y. Instead of 3 halves, comma 0, I'm going to get 0, comma 3 halves. Sorry, the labeling here is a little off. And I'm going to graph that line. Look like... And there is my graph of f inverse of x. And it should look like you have reflected the original graph across the line y equals x. So just to kind of show you that, if I plot the line, if I dash the line y equals x, right? Yeah, it exactly looks like I took that blue graph and flipped it across that line y equals x to get the red graph. Cool. Just to kind of confirm that this really is what we get, if we do want to find the inverse function, I'm going to have y equals 2x minus 3, interchange x and y, solve for y. So y should equal 1/2 times x plus 3. So there's my inverse function. And you can see, hopefully, that if you plug in negative 3 for x, you get 0 for y. And if you plug in 0 for x, you get 3/2 for y. So we definitely do get those coordinates. Cool. Yeah, that's kind of it. So when you're graphing an inverse, you can totally just interchange x and y to graph the inverse. And here's that example from before that I'm going to show you again. So since we find inverse functions by interchanging x and y, we are effectively interchanging I forgot what I was going to say here, to be perfectly honest. The blank and blank. Oh, I know what it was. So remember, the domain of a function is all the x things. The range of a function is all the y values. So if we're interchanging x and y, we're effectively interchanging the domain and range of functions and their inverses. In that example a minute ago, for f of x equal to x squared plus 9, where we were given that x was greater than or equal to 0, we found that the inverse function was equal to the positive square root of x minus 9. And we also had a domain of x being bigger than or equal to 9, right? Just graphically, we could see that. So I'm going to point out that the domain of f of x here, which is x being greater than or equal to 0, is the same as the range of f inverse of x. And again, I'm just thinking graphically, right? Here's f of x. The domain is all x greater than or equal to 0. Here's f inverse of x, where the range is all y values greater than or equal to 0. So in this example down here, the domain of this function is 0 to infinity inclusive of 0. The range of this function is 0 to infinity. And similarly, the range of f of x is equal to the domain of the inverse function. So here, just looking at the y values here, the lowest y value is 9. So my range goes from 9 all the way to infinity. Same deal for the domain here, right? If you look at this function here, x minus square root of x minus 9, we know that x has to be bigger than or equal to 9. So my domain here is exactly everything from 9 onward. And this is true, right? If you're interchanging x and y, you're interchanging the role of the domain and the range. Well, that's great because now we have a different way of finding the range of a function. If I want to find the range of f of x, I can find the domain of f inverse of x. That is often how we find range. Let's look at some examples. So this means, like I said just a minute ago, we can find the range of f of x by finding the domain of f inverse of x. So let's find the range of f of x equal to 2 over x plus 3. So let's see here. So I'm going to find the inverse function. So I'm going to start with y equal to 2 over x plus 3. I'm going to interchange things. So x equals 2 over y plus 3. I'm going to solve for y. X minus 3 equals 2 over y. Okay, fun fact. I could do what I'm about to do, multiply both sides by y, then divide both sides by x minus 3. So I'm going to do that, but I'm going to show you a faster way. So here's the long way. You can say, great, x minus 3 times y is equal to 2, and then divide both sides by x minus 3. I don't want to distribute this here. So y equals 2 over x minus 3. The faster way, if you have something over just y, is to just take the reciprocal of both sides. So 1 over x minus 3 equals y over 2. And then multiply both sides by 2 to get exactly y equals 2 over x minus 3. Either way is fine. Okay, so my inverse function here is 2 over x minus 3. And we can see that the only problem value of x is x equal to 3, right? If we set x minus 3 equal to 0, we want to exclude x equal to 3. So 3 is excluded from the domain of the inverse, which means 3 is excluded from the range of the original function. So the range of the original function f of x is everything except for 3. It's negative infinity to 3, union 3 to infinity. I will point out, if you look at this original function, 2 over x plus 3, you can see that that function can never equal 3, right? If we tried to set 2 over x equal to 3, let me just write this over here. I think I have enough room, yeah. So if I set 2 over x, if I set 2 over x plus 3 equal to 3, subtract 3 from both sides, you get 2 over x equal to 0. And then if you multiply both sides by x, you get 2 equal to 0, which isn't true. There's no solutions here. 2 divided by anything is never going to equal 0. It can get really, really close to 0. Like if x was a billion, 2 divided by a billion is super small, but it's not 0. Okay. Let's do the same thing for this next one, which is a little bit more work. So we're going to find the range of g of x equal to 6x plus 1 over 2x minus 9, again, by finding the domain of the inverse function. So we're going to say first y equals 6x plus 1 over 2x minus 9. We're going to interchange all the y's to x's, all the x's to y. So we get x equal to 6y plus 1 over 2y minus 9. This is one where you do have to be more careful. So here we can't just flip both sides. We're going to multiply both sides by the denominator. So we're going to have 2y minus 9 times x equal to 6y plus 1. Sorry, I figured right. This is step 3. You don't really need to write down these step numbers. I just like to do it so I'm consistent. So now solving for y, distribute the x on this left-hand side. So you have 2 times y times x minus 9 times x equals 6y plus 1. We want to combine all the things that have y's on one side, all the things that don't have y's on the other side. So we're going to rewrite this as 2yx minus 6y, so subtracting 6y from both sides, equal to positive 9x plus 1, adding 9x to both sides. The reason we want to get all the y's on one side is so that if there's more than one y, we can then factor out a y from everything. So we're going to rewrite this as y times 2x minus 6 equal to 9x plus 1. Divide both sides by whatever's multiplied by y here. So y is going to equal 9x plus 1 over 2x minus 6. And then finally, we rewrite it as g inverse of x equals 9x plus 1 over 2x minus 6. And then, kind of accidentally, I didn't mean for this answer to be the same as the previous one because they're not necessarily the same. They just happen to be here. If I want to find the domain here, the domain I'm going to exclude where 2x minus 6 equals 0, which is going to be, again, x equal to 3. So the range of g of x is going to be the same as the domain of g inverse of x, which is everything but 3. So again, everything from negative infinity to 3, union 3 to infinity. And again, just a poor choice that both of these happen to be the same, such is life. I will point out, if you try to set this equal to 3 and solve it, you will get no solution. And it's kind of neat to see. Do I have enough room here? Not really. I encourage you to, so yeah, let's do it again. Let me grab your stick real quick. So I think it is worth seeing just so you can kind of be like, oh yeah, 3 really isn't in the range. So we set g of x, which is 6x plus 1 over 2x minus 9 equal to 3. Look what happens. Multiply both sides by 2x plus 2x minus 9. You get 6x plus 1 equal to 3 times 2x minus 9. Multiply out the right-hand side. You get 6x minus 27. The 6x's cancel, and you've got 1 equal to negative 27. That's not true. So this original equation has no solution, which means the original function can never equal 3, which means 3 isn't in the range of g of x. Any other value is, though. So if you did that equation set it equal to like 4 or 5 or negative 2, you would be able to find the solution every time. All right, we're almost done. Last page. So this one is similar to that other example we had where we had a function that isn't invertible everywhere, so we had to restrict its domain. Same kind of deal here. We're still going to find the range. So I will point out, you can totally find the range kind of the old way we used to do this by saying, okay, well, if x was 0, 10 divided by 0 plus 5 is 10 over 5, which is 2. And that's the biggest this can be because I'm making the denominator as small as possible. And if I let x be any larger, this numerator, this fraction is just going to get smaller and smaller and smaller. So I'm expecting the range to be everything from, not a bracket, a parentheses, from 0 to 2 with a bracket. I can get really, really small if x is really, really big, or I can get equal to 2 if x happens to be 0. But since this is x to an even power, this denominator can never be smaller than 5. But let's do it the other way. So I'm going to do it by finding the range, sorry, the domain of the inverse function. So y equals 10 over x to the 4th plus 5. X is bigger than or equal to 0. Interchange all the x's and y's. So x equals 10 over y to the 4th plus 5, but now y has to be bigger than or equal to 0. Solve for y. So let's just do the thing where we take the reciprocal of both sides. So 1 over x equals y to the 4th plus 5 over 10. Multiply both sides by 10. So 10 over x equals y to the 4th plus 5. Subtract 5. Oh, sorry, I forgot to write y greater than or equal to 0. Y greater than or equal to 0. And then we have, I'm going to switch sides. Y to the 4th equal to 10 over x minus 5. We still have y being bigger than or equal to 0. And finally, y equal to plus or minus the 4th root of 10 over x minus 5. But now here, we have to say that, well, since y is bigger than or equal to 0, we know it has to be the positive root here. So here's what we've got. We've got that f inverse of x is equal to the fourth root of 10 over x minus 5. Now, if we want to find the domain of this, we're going to say, great, to find the domain, sorry, I'm a little froggy over here. Find the domain, we're just going to say, great, 10 over x minus 5 has to be bigger than or equal to 0. It's really unsafe to add 5 to both sides here. What we need is a common denominator. So we really have 10 minus 5x, sorry, 10 over x minus 5x over x bigger than or equal to 0. So we have 10 minus 5x over x bigger than or equal to 0. So then we're going to use a number line. And on the number line, we have 0 because 0 makes it undefined. And 2 because 2, if we plug in 2, 10 minus 5 times 2 is 0. Pick a number bigger than 2 like 3. 10 minus 15 is negative. 3 is positive, so it's negative overall. Pick a number between 0 and 2 like 1. 10 minus 5 is positive. 1 is positive. Pick a number between smaller than 0 like negative 1. 10 plus 5 is 15. Divided by negative 1 is negative. So I exactly want this. I don't want 0. I do want 2. And that's how I'm getting everything from 0 to 2. So my domain of f inverse is everything from 0 exclusive to 2 inclusive. So my range of the original function is exactly 0 to 2. Very last thing. We kind of hit on this a little bit before, but didn't spend a whole lot of time on it. So if f of x is invertible, and we're just going to assume it is, so given f of x equal to x cubed plus x plus 6, it is invertible, but we can't really find the inverse. I want to find f inverse of 6. Well, if f inverse of 6 is equal to, let's just call it a, that means that f of a should equal 6, right? If we interchange the input and the output, we interchange, but I should say the inverse function interchanges the input and the output. So we're looking for a number that we could plug in for x and get an output of 6. Well, I think I see an obvious choice. If a was equal to 0, 0 plus 0 plus 6 would equal 6. So it looks like a has to be 0 because f of 0 equals 0 cubed plus 0 plus 6, which is 6. So if f of 0 equals 6, that means f inverse of 6 has to equal 0. In a similar way, if I look at f inverse of 8, well, I think if I plug in 1 for x, 1 cubed plus 1 plus 6 is 1 plus 1 plus 6, which is 8. So it looks like f inverse of 8 is equal to 1 because f of 1 is equal to 1 cubed plus 1 plus 6, which is 8. Similar idea for f inverse of 16. I would encourage you to try to guess this one for a second. What number can I plug in for x that's going to give me an output of 16? Well, I think it's going to be 2. I'm pretty sure it is. Check though. That's because f of 2 is equal to 2 cubed plus 2 plus 6, which is 8 plus 8, which is 16. So that's how you find f inverse of something, is you try to guess the number you plug into the original function to get the output you were looking for. All right, that's it for homework number 13.